So welcome to my last talk. In the second part, I have shown you some proofs. And then I wanted to show you the whole thing problem proof that it is undecidable. But at the end, I recognized I missed myself some details. So I would like to show it to you shortly before I start with the last part. So the problem is to decide whether there exists an algorithm such that you put in any problem that is a program with an input. And this tells you always whether this program with this input will not terminate or whether it will hold after a finite number of steps. And I want to prove that there is no such algorithm. So I will assume that there is one and lead it to contradiction. So what happens now is I make a transformation of this program. And this transformation will behave with respect to termination exactly the opposite than the input, P. That is what I called yesterday the negation of the program. So that means if this oracle says that P will not terminate, then this modified program will terminate. And if the oracle says that P will terminate, then my program will loop forever. Okay? So this program, let us call it K, will terminate if and only if P does not terminate. That's why let us call it the negation of P, so I name it K. Okay, now you can give K any input. So one main step was negating, and one main step is putting itself to the side. So the system can talk about itself. So I can also put in K as an input. Okay? So if this oracle exists, now what happens? There are two possibilities. Either K terminates or it does not terminate. Okay? So what happens if K terminates? K terminates, then H will report hold. So then K will not terminate. Okay, do you see the contradiction? That means my assumption K terminates was wrong. So the only possibility is that K does not terminate. But what happens then? Well, then H will say K does not terminate. So K itself will terminate, which is not possible. So never mind whether K terminates or does not terminate, I get a contradiction. That means my assumption was wrong that there exists such an algorithm H. And it is simplified. So if you assume this is now a Turing machine with an input, then of course it is a bit different. I also have to handle the input, but this is the main idea. So very simple. This is nice or not? Okay, it is leaving out all the details. And of course, once you know, you can make it nicer. So it is a very big achievement to find this proof. But this is what I mean with beauty. Okay, this is an elegant, small core of the proof. Okay. And today I would like, after I have talked about timed automata, by simulation, abstraction, some of you were a bit overwhelmed if you do not know much about this topic, but at least you got the taste, I hope. And then yesterday I have shown you some proofs of decidability and undecidability. This is also perhaps something you was not confronted yet, but it is very important for training the brain to see these aspects. And today I will talk about that. What most of you expected from me in this summer school, it is the reachability analysis using flow pipe construction. So, as you know, there is a long list of tools that do reachability analysis for hybrid systems, and this is incomplete. I did not put timed automata tools, there are a lot, and also I did not mention all of them. Perhaps these are the most well-known or popular ones, and in my group, there was FlowStar developed, and HyPro is the newer one. FlowStar can handle also nonlinear differential equations. HyPro is designed only for systems with up to linear differential equations. But then now you can ask, so what do these tools do? How do they compute reachability? And there are different classes. One class of them, was just mentioned by Walid, is rigorous numerics. So they use rigorous simulation. That means kind of simulation-based approach, but with guarantees. So also they over-approximate trajectories. And then here a short picture from an Acumen run. And there are a number of tools, also Estaliro we have already heard this week. And other tools use deduction. So they axiomatize what is a hybrid automaton or hybrid systems. They axiomatize what is the semantics, and then they derive. So you know these deductive rules. You say if that and that and that holds, then I can derive that something else holds. Perhaps what most of you know will be the resolution system for propositional logic, which from two clauses, one having X, one having not X, can derive another new clause. And this is a complete proof system for propositional logic, just having one rule. So based on those axiomatization, you can use theorem provers and then some semi-automated procedures to compute reachable sets, mostly based on invariance. So that is the hardest task, to find invariance, but some they can find automatically. Then another set of tools use satisfiability checking. So these are the basics are tools which you give a formula, existentially quantified or quantifier free, and then it tells you whether there is a solution. This is called satisfiability checking. So SAT solving and SAT modulo theories, SMT solving tools are from this class. And now you can enrich. Usually these tools are for different logics, but it does not include differential equations. You can enrich them with a technique what is called interval constraint propagation, which just kind of propagates domains for variables to restrict domains. And then you can use those to decide whether certain areas are reachable by encoding logically passes of the system, basically. You write a formula. The solutions are computations of the system. And then D-reach is one of the D-reach and HSOV and ISAT. ISAT and ISAT-OD are the most well-known tools from this class. And then there is one more class, or more classes, of course, but this is the last one I mentioned today, is the flow pipe construction-based methods. Flow pipe construction is something not well known, actually, only in this community. So better known is forward reachability analysis. Okay, this you know all. So you start from a set, compute what is reachable in one step, in two steps, and so on, and represent those sets, and then check what you can reach from it. But of course, for hybrid systems, these sets are highly complex. So what these methods do is, if assume that you start from this set, and this is the set of the trajectories you can reach, this method kind of pave these trajectories. Here, for example, by boxes. So hyperrectangles, you compute a set of hyperrectangles such that if you build the union, then everything is in it. This way it over-approximates. Theoretically, you can also under-approximate that, but that is much harder. So there are no methods efficiently doing it. There are theoretical methods, but in practice, mostly they do not work. So there are some tools. We already heard SpaceX, Flowstar, and also Hypro from our group. And you see, if you start in some initial sets, now I do not know, I think it is converging to starts from the inside and converging out, or the other way around. So you have a set, and then you compute a sequence of sets. In this case, I think it is sonotopes. And then all the union of these sets, somewhere the real behavior is inside. And here you see two other, one with the polytopes and one, I think, with oriented rectangle. These two I took from these sources. So, and what I would like to tell you today in the remaining time of my talk is how these are computed very intuitively. So very intuitively, you start with a hybrid automaton, as I have shown you at the beginning. Then you have set of initial states, and you would like to know whether a set of target states is reachable. So you start with what is usually called a weighting queue. These are a set of states for which we will compute successors. And here in R, we will store a set of states whose union covers the reachability within a certain amount of time and jumps. So now we always take an element from the queue whose successors we need to compute, as long as it is not empty and some other conditions are not yet satisfied. For example, if I want only to compute for a certain number of jumps, so discrete transitions, or a certain number of total time, or whatever, or some resources like timeout. So I will take the next set for which I need to compute successors, compute its successors, let us call it reach of P, in one step. By us it will be, you start in a certain control modus or location, compute the dynamics according to differential equations, and then compute whether you can take any jump to another control modus from this whole, what we call flow pipe. This is included here. Reach P are the time successors, and then we compute jump successors from the time successors and put them to Q, because for them we again need to compute successors. And once we terminate, we take, sorry, this should be R, no, P from R, exactly. All sets from R, unite them, and if any of them intersects with the target, then we return yes, otherwise we return no. Okay, so normal reachability, forward reachability, nothing new. But now, for hybrid automata, we have some special challenges. Namely, the first one is, what is this? So you have a set of states. And if you talk about programs, then you can describe perhaps by formulas like x is larger than 0. Or if you have timed automata, then you can have these regions then that we described yesterday, or the day before yesterday. But now for hybrid automata, these sets are highly complex also from the shape. They are nonlinear, they are not convex, so not nice. So we will use over-approximative representations, and with representations I mean a shape and a data structure. I will come to it. And then once we have some data structure for these sets, we need to compute things like checking for emptiness. Then here we have a union, intersection. And here in reach, we will need also further operations on these separate set representations to compute successor sets. So let us look at these three questions, starting first how to represent state sets. So there are some well-known representations where we know how to compute. There are also some others which are not on this slide. Hyperrectangles, we already know from I talked yesterday. These are just in each dimension you have an interval and take the cross product. Where you can represent boxes, state sets by boxes, the only thing is if you have some state set like this, and then you have to over-approximate it by a box, then you see even if it is tight, the over-approximation can be quite big. Okay, so this is the disadvantage. In general, large over-approximations. And if you have a long set and over-approximated box, it can even be worse. But it is very fast. And then we have also other sets like you can turn boxes in the space. Or you can have in general polyhedra, which are more precise or can be arbitrarily precise, but also more complex to compute with them, and so on. We already heard sonotopes. We already heard support functions. Flowstar uses Taylor models. And now if you take any of these representations, or these are not yet representations, these are geometric shapes or some ideas how to represent, you still need a data type. But once you have the set, in the data type you need also the functions, the operations on the data, and this must include intersection, union, linear transformation we will need for the reachability computations, Minkowski sum, which if you are not well known with these operations, Minkowski sum is basically the sum of points from two sets. So you take a point here, and if you sum them up, it will be included in the result. We call it also bloating, this operation, because you see, if you have here this set and add up this one, you will add up this triangle because its corner is now at the 0. You will add it up to each point here. So basically, the borders of the set will be bloated by this triangle at all points. If it is this set, the left corner is not at 0, then it will also move the set. And then we need some further operations. So let us look how to choose one of those representation types. It is very important. It is very important not so much for theoretical reasons, but for efficiency reasons. So if you choose a certain representation that needs some memory, so if you see a polytope or a polyhedra can have a lot of vertices, for example, then you need a lot of space and you have to compute with it, whereas boxes, if you store two corners, it is sufficient to represent the box uniquely as a data type. So the operations that you perform depend also partly on the size of the memory requirement. But of course, if you invest more in computations, you can also get more approximate results. So it's always a balance. You have to choose which one you want, and then you get something at the cost of something. Let us look at as an example at polytopes. So you know what is a polytope? It is based on half spaces. So half space is just a linear inequality in the space. And the polyhedron is an intersection of finitely many half spaces. This can also be open. And if it is closed, then we call it a polytope. This is, for example, a polytope. And this is just a geometric object. Now we need to store it in the computer because we want to compute with it. So we need a data type. And for example, for polytopes, there are two popular representations. Either we store all the vertices, so in this case I would store these 4, or we store the linear equation system that defines this object, so the set of these inequations. And this would be, if I go back to these vectors, basically, so the normals and the positions of the half spaces. And depending on which representation I take, some operations are easier to compute, or some operations are harder to compute. Unfortunately, none of the two representations are ideal for all the operations, as you would expect. So what is easy to say without needing much time is the union. If I have the vertices, and I have two polytopes where I know the vertices, the union is not a polytope anymore. So we compute the convex hull of the union. So if I have, let me take two boxes, these are also polytopes. So if I know the vertices, then you see that the union, the inside is not a polytope. So we always compute the smallest polytope that contains the union, and this is the convex hull. And computing the convex hull, you see that the vertices of the convex hull are vertices of the original, whereas the facets, not. So that's why computing in age representation, where I store the half spaces, is expensive, because I have to compute these new facets, whereas the vertices I can just unite, though it is then not minimal, but it doesn't matter. I can reduce it later if I want. Whereas for the intersection, you see this in the middle, the half spaces are all there. So basically, I only have to unite the inequalities, but there are new vertices which I need to compute. So that's why union and intersection, one of them is better than the other, but there is no golden way. OK, So now I would like to show you, when I have these data types, how can we do reachability analysis with these data types. And first I will show you an easier subclass where basically this is similar to rectangular automata, so that the derivatives are boxes. They are constant from a box as a set, so no differential equations later in linear differential equations. Only x dot equals a constant, or x dot is from a box. And all other conditions are linear. So the invariants, guards on transitions, and the resets are all linear, defined by linear formulas. And in the second case, we will do the same, but we allow as derivatives linear differential equations. OK. So let us look at the first case. And if I have an initial set, first I need to compute what is reachable by time. And then I get a flow pipe, as we call, and I need to check which jumps I can take from that set. So let us first look at what happens if time evolves. The derivatives are given. So these are, assume we have two variables, x1 and x2. And here, if I take a point, then this is the derivative for x1. It is a constant, and this is for x2. So what we know that for each point inside, this is the initial state. I wanted to show it here. So for each point here describes the derivative of x1 and the derivative of x2. What does the derivative mean? Means change of the value per time unit. And this is constant. Means if I choose here a value for the derivatives, then the vector here describes me the change for one time unit. And I can stay there without considering the invariant for arbitrarily long. Also for below one time unit or above one time unit. So that means that if I take, these are the derivatives, I can take any of these vectors, especially at the corners. These describe change one time unit. I can also scale these vectors down. Then I get below one time unit, or up. Then I get above one time unit. OK? And all these vectors are possible changes for a certain duration. So what do I get is what we call the cone of Q. Each point or vector inside of this cone is a possible change. So how to compute now from this initial set with this possible change? It is the Minkowski sum. So I take this and add up this cone to all points of the initial set. And then I get this green area. And this is the sign for the Minkowski sum computation. OK, so this is what I can reach by time, unbounded time. Now, the time might be bounded because we have an invariant. So now we need the intersection. Assume in this red box, the invariant holds. So now we apply an intersection computation. And for polytopes, this means we have here two new facets, and this inner part will be the part which is reachable by time from the initial set. And now we compute what we can reach from it by discrete transitions. Each discrete transition goes from one location to another one, has a guard and a reset. And the guard is in general a linear function, which is a linear conjunctive function. That means it is a polytope itself. So we just need intersection computation. In this case, in this part is the guard. So the intersection will give us this red part. And once I computed that, I need to apply the reset. And this is a linear transformation, because we assumed it is a linear. So each variable is set to a linear expression, which is a linear transformation. Sometimes it is even easier, like I set here to an interval, I could compute without applying explicit linear transformations by first making x2 free. So I project the set to x1 and build its composition with R. And then I intersect it with the x2 area to which I set the variable. And I get that set. Okay? So what you see here is a set of operations or a sequence of operations that I need to apply, and then I get the time successors and the discrete successors. And because it is forward computation, for this class of systems, it is unrestricted in time duration per location, but it is restricted in the number of jumps because, of course, I cannot do it forever unless I find a fixed point by remembering the sets that I have reached before, and then if my new set is included in those, then I can stop, do not need to compute successors for that. But fixed point detection is very expensive, so that is another question. Basically, it is what we call jump-bounded computations. So now, if we have, instead of x dot, the derivatives are from a box, now we have linear differential equations. And then you say, oh God, now it is getting complicated. It is not that complicated. There are only some black boxes you need to believe me, which I will not explain. I just will give you the meaning, but not how to compute it. And then it is easy. So assume we have an initial set, this blue one, x0, and we want to compute what we can reach from it by time. And now we cannot compute it for arbitrary time. We need to restrict also the time interval. So assume it is a certain interval, and assume this is the flow pipe that I can reach from this set within this time. And now you see, if I would use polytopes, the smallest one would include at least this set, so it would be strongly over-approximating. So instead of computing it for all, we build so-called segments, time segments. So first, this is the time step. So first I compute what we can reach within delta, then from delta to 2 delta time, from 2 delta to 3 delta, and so on. To be precise, I cannot compute that. This problem is undecidable already. But I can compute over approximations. So what I want is compute a sequence of sets that contains all those sets. OK, how to do it? The first flow pipe segment from 0 to delta time is a bit more complicated. So I start here by the initial set and want to compute what is reachable within this time interval. This is a bit more complicated, and the further steps will be easier. And there are different approaches. I tell you just one approach. This is not the only one how you can do it. So we start here, and now the first black box that you need to believe me is that the solution for this differential equation, starting from a certain point, if you want to know what you can reach, what you reach in exactly delta time from a point here, you need to compute for this matrix. Let us forget about the BU first. Let us take this blue one, x dot equals ax. That means it is a linear transformation, what you reach in t time, or in exactly delta time. And to know what you reach, you need to compute this matrix exponential. There is a paper, 99 ways of computing the matrix exponential. In general, this sum will not stop, so sometimes you cannot exactly compute it. But sometimes, if you have luck, after some points, at some k, this component gets 0, and afterwards it remains 0. So we try to compute it as good as possible, and then the time successor at time delta, at, not within, is by applying this matrix exponential as a linear transformation to my original point. Okay? So now this set here is what you can reach at time delta. Now what we want to compute is what you can reach within time delta. How to do it? Now the first guess could be, okay, we work with polytopes. Let us build the convex hull. And this is the blue one. But you see that this linear transformation has the property that if you apply it to different values from 0 to delta, this dynamics is not linear. So by building the convex hull, it is not sure that I include all of them. And now I need to solve basically an optimization problem. I need to solve what is the biggest distance here between this linear behavior and the nonlinear one. And there are techniques to do it over approximatively, either depending on the initial set or independent. If it depends on the initial set, I always have to recompute. If not, it is bigger. But basically what I do is I compute a box such that if I bloat this at time delta with this box and build then the convex hull of the initial box with it, then I over-approximate the dynamics according to x dot equals ax. So what I need to be able to apply linear transformation and Minkowski sum. And I need to be able to compute this box, but okay. But now there is still this BU. What is this BU? Well, you can look at U as control. You can look at as disturbance. Important is that it is not arbitrary. It is bounded. We assume it to be bounded. And we want for worst case behavior. So for all possible U. That means we have here a domain for this U. B is a matrix. And then we can compute another box such that if we bloat that set also with this other box, which takes care that all these disturbances within time delta are included, and build the convex hull. Then now I have an over-approximation of the whole dynamics. So you see, this is the first from 0 to delta. And now I want to compute also the other sets, so now delta to 2 delta. And I told you that now we have an easier task. Why? Because if the first set already contains all of that, then each point here can be reached from here by exactly delta time. So it is just the linear transformation part and not the other one. So I apply the linear transformation for time delta. And this is the over-approximation for x dot equals ax. But now I have this disturbance BU. So I need this second box that I computed. It is the same one. Bloat it, and then I have the second segment. So this is how this flow pipe construction-based method works. And the flow pipe is a sequence of these sets. And then we have, for the guards, intersection, the same as before. So the second step is the same as for the class before. We intersect those. And then to the intersection where the guard is satisfied, we apply a linear transformation and then continue. But now what you see is, for the previous class, we had one set for the flow pipe because the behavior was linear. But now we have a sequence of sets, here 3. That means you have a more strongly increasing tree widths in the search, because now I need to compute the successors for all 3. So this does not work in practice. That's why people usually over-approximate either already here before the linear transformation or after the linear transformation, over-approximate and continue with one set. So if you look at the global picture, I start from a set, compute the flow pipe within time t For each outgoing jump, I compute the intersection. Then I, what we call a cluster or aggregate those sets, the intersected ones, apply the linear transformation, and continue again. How much time do I have? So afterwards, this is the tree. This is the tree. And here, if they come from the same flow pipe, then some of them will not have any intersection with jump cards. Some of them will have. And if they are for the same jump card, then we can aggregate them and continue on. But still, several jumps can be enabled, and we have a branching. So here, from this, for example, I can take several different jumps to different locations where you have different dynamics so that you cannot aggregate those. So we have a tree. Now the two tools from us, the FlowStar and HyPro, use these methods, whereas with Taylor models used by FlowStar, you can approximate also nonlinear behavior, so nonlinear differential equations. It is not fully the same approach, but it is similar. Because Taylor models are a bit different, so if you have here, it is not so very visible, but there is a green line. This is the original. And now we do basically Taylor approximation of it to a certain degree at a given point, and you get the red one. And then it is bloated by adding up this interval or this box at each point. It seems that it is smaller, but this interval is the same everywhere, okay? So we add up this cube around the function, which assures that within a given interval, the approximated function is inside this tube. And then if you start here, then you know that at the end, if you start at this point, then you know that at the end you will be there. And the other tool, HyPro, actually it is not a reachability analysis tool, but it is a library. It offers an implementation of many of the state set representations and operations on them that you need in reachability analysis. And it is sort of not to be the fastest, but to help you if you want to implement a dedicated method where a tool, a black box tool, is not sufficient because you need some extension, you need some dedicated adaptations, whatever, then you can do it. So it is available, open source C++ library, and the structure is, firstly, what is important also, the question was in the last talk, what is the data type for the numbers? It offers both. You can compute with inexact and with exact numbers. And we offer even a mixture of those such that we compute first inexact, and then if it is verified by an exact computation, whether that is the inexact computation gave an exact result. This is very important, for example, if you work with polytopes and compute intersections, and then you need to compute whether an intersection is inside a set or outside to know whether it is a vertex or not. And then if you are at the boundary, but you go a bit inside, then this will be thrown away. So then it is very important for optimization that we compute exactly, and for that we have several solvers which we use in combination. So GRPK is inexact but very fast, and these are SMT solvers and LP solvers which we use additionally. Actually, SMT that is R, and Z3 is the most well-known one. And beside polytopes, we offer also boxes, tonotopes, support functions. So basically, the mostly known representations which share a common type, so it is easy to exchange those in your implementation. Whereas some do not fit to this interface, so these two do not share the interface, and we can convert between them, either exactly if possible or over approximatively. And then we have some data structure for additional stuff, like for example for hybrid automata. You can use some logger and plotter for visualization of the results, and then the algorithm can also use some parser, and we implemented also reachability analysis tool in what is called Hydra. So Hydra uses HyPro, and before I come to Hydra, so this is the illustration boxes we know. So these are just in each dimension you have the intersection of intervals. Polyhedra I already mentioned. Sonotopes you already explained with the center and generators. Support functions are a kind of lazy evaluation of operations. So you have some set, and then you apply transformations to it, or operations, by just storing the operations but not executing them. And if you need to know what is the intersection with a certain hyperplane, for example, then there are some tricks to transform the operation back to the original set and compute them. Then orthogonal polyhedra is one of the few non-convex representations that are possible, and they do not share the interface because we still do not know how to do Minkowski sum computation efficiently on that, and Taylor models are also implemented. Here's an example in this reachability analysis algorithm, what I explained you. So here's a hybrid automaton with a certain initial set. This is this one. And we have a linear differential equation set. And if I apply the time transformation, this one is what you reach in exactly delta. Linear transformation according to the matrix exponential of this matrix, 1, 4, minus 4, 1. Then we build the convex hull. Then we build bloating with the first box to include nonlinear behavior, which is very small, so it is nearly not visible here. This is the convex hull of the two. And then here we do not have this BU, so the disturbance. So the second bloating falls away. And then if we do it for the whole flow pipe, this is here the invariant. X is larger or equals 0. So I compute these one after the other and build the intersection of each flow pipe segment with the invariant. So here it will stop. After a time it will get empty. And then I have also a jump which has a guard. So I intersect all of those with this green area. This is the guard. So I will have here a set with a non-empty intersection, and then apply a linear transformation to it, and I get this set. And then I continue, apply again the flow pipe computation, I get again a sequence of sets. And as you can imagine, now this delta for the segmentation, if it is larger, I compute fewer sets, so it's faster but more inexact. So the error can be reduced by reducing this delta and by changing the state representation. But they are still very expensive. So I would like to show two examples how you can use this library to compute something dedicated. Not a general off-the-shelf approach, but something that can be applied to your problems. So this is the way as we compute flow pipes or over-approximate them, that we have these segments that over-approximate the behavior in certain time. But often in the systems you have, for example, control variables which are discrete, or you have just clocks which measure time. So you can handle them differently. We have seen how tidal automata can be model checked. Today you have seen if the derivatives are constant, you can apply a different method as if the derivatives are linear differential equations. So we can try to partition the state space into subspaces where I can compute successors locally. For example, for discrete variables are those whose derivative is always 0. These are, for example, variables from your control program, which do not change by time. They change only when the control program does a step. For them, the flow pipe computation is easy because they do not change, right? But if you consider them together with the others, it blows up the dimensionality. So you could handle them differently, or you could handle clocks differently, or other things. But of course, it's not trivial how to cut them apart such that we can still compute successors. And this is possible in the case if they are what we call syntactically independent. So if you have two variables, they do not appear in the same constraints. So for example, you have two variables x and y. They are never compared. You never set x to something that depends on y. Then you can divide the derivatives into two sets of constraints which do not share variables. You can divide also the invariants in the conjunction of two formulas which do not share variables, and you can do the same with the guard and the resets. Then we can cut them apart. And really often this happens, so that the systems are only connected by time. Of course, they are connected by time. And to be able to synchronize in time, these flow pipe segments all represent the time initially within delta, from delta to 2 delta, and so on. So for example, if one of these sets gets an empty intersection with the invariant, then we know that here all others also stop because the set gets empty, the global, the composition of those. So it is not that I completely independently analyze them. I only keep their relation in time. And this is often sufficient to get a good over approximation. And the last example I would like to mention you is I showed you different state set representations and said boxes are very fast and polytopes are slow. But they have also, for example, support functions which are sometimes very good, sometimes not so good. Depends really on your example. So if you want to use one of those representations and it does not work, for example, you use boxes with a relatively big time step length, and then you get a non-empty intersection with some unsafe state set. Then you do not know whether your system is safe, because this intersection could be due to the system is really unsafe, the unsafe state set is reachable, or because you had a too big over approximation, what is not seldom if you use boxes. And then in that case, you have to restart the whole analysis with something. For example, here you could use support functions with a smaller type step. And if you still have some non-empty intersection with the unsafe state set, you can use polytopes with a high number of facets or whatever. And you hope that here you can verify that you do not reach the unsafe state. But each time you have to restart. You have to redo everything. Now with this library, we implemented something which does it only as far as it is needed. So for example, if we start from this A set, we start with this computation of boxes. And we get some jump successors. This A set is OK. Successors are computed, no intersection with unsafe state set. Now I continue, for example, computing successors for C. C is OK. Successor is D. I compute also successors for D, but for example, I reach the jump depth lengths, so no further successors. This part is OK. So I start with B. It has two successors, E and F, but no unsafe intersection. E has one successor. It is safe. And computing the successors of G, I reach the unsafe state set. So what to do now? I refine the computations, but only as far as it is needed using this representation, only on this path, because I just want to refine it such that this counterexample is eliminated, because the over-approximation error is reduced. So only here I use this from the root to recompute this path. Now what happens? I could remove the counterexample. I still have to compute successors for F. I do it, and I again get a counterexample. And now, because here I already refined, I only have to look up from where do I need to continue the refinement, so only this one. And this is nice because we stored a lot of work. And it can be that it still contains a counterexample, so I move on to the next representation, and I will only refine this path. And if it is now safe, then I'm done. So instead of repeating the computations 3 times, I really used a minimal repetition or a minimal redoing of work in order to exclude counterexamples. And now you can take your problem and think of what is the best, and then you can use this library according to these examples. There's also help to see how to use the library. We also implemented parallelization, for example, which is also not so hard, but also not trivial for this refinement tree. So we have an implementation now for this refinement tree with parallelization. And it is quite good. We are getting better and better. Of course, this tool is quite young. The first release was last year. But if you like to look at it, if you need any help, then just try it and drop us a message if you would like to discuss about it. OK, I hope I am this time in time. Thank you for your attention, and I hope you enjoyed the talk.
Thank you very much, Erika. Any questions from the audience?
Yeah, I think I saw the FM presentation some time ago about the library and stuff. So what, is there an input syntax, or do you just write things in terms of the data structures?
It takes, I think, SpaceX syntax.
Okay.
So there is this parser with supports. And we also tried this HSSCPS tool.
Okay, yeah, that's our tool.
Yeah, we did not try it last time. At the beginning, it had some Kinderkrankheiten, so this children's disease. In the meantime, I did not. We also reported some problems by the transformation. We did not try it, but I think it is not much better.
Okay.
I've heard. So we did not try it yet, but. Yeah, that it is a very, very, very interesting work, this transformation. Also because the models are, of course, not the same expressive. Some support, for example, arbitrary dynamics, x dot equals star, or unbounded. Some support urgent transitions. Some allow non-convex guides. So very complex to transform, but we support SpaceX, and I do think also FlowStar, I'm not sure.
Okay.
It's very hard to find a common denominator,
Yeah.
or the right common denominator between all the different tools.
And it is also, we must say, if you do implementation work, this is highly valuable, extremely time consuming, and not well paid in terms of publications.
Yeah.
Okay? You work a year or two on something like this transformation tool, and you get one paper out of it.
Yeah.
If you are lucky, and if the reviewer says, well, there is no scientific contribution in it. So we really should think of appreciating more these tools, and that's why, for example, the Arch workshop is dedicated to benchmarks, which is also very important. Without benchmarks, you cannot test anything, right? But where to publish benchmarks? So that is very good, and also tools. We have the SNL workshop, where we devote to symbolic and numeric computations, where tools are also highly appreciated. So
It's really good that you mention these because they're very important for the community.
yes.
ARC and SNR.
Yeah, I have questions. Why you it's not as efficient as other tool? I expect
They're
that each
yeah.
component could be more efficient because you can add more optimization in there.
So sure, but there are two things. So firstly, there's only one person working on it. It is Stefan Schupp. Shin should have done this work, but he decided to do Taylor models, and then Stefan had to finish the work that was not done, but was expected by a project.
The exciting things.
So he works on it like now 3 years, and if you develop a tool like SpaceX, it's already a long time there, improved by a lot of work, and it uses a certain representation. Now we have to do it for several representations, and we do not connect them, the different representations in the tool, by fixed wires. So, of course, we can improve Hydra, but
I think that, for example, when you say that it's not as efficient, is the you need to have some kind of fair comparison.
yeah, and
you
it
need
is very
to,
hard.
To compare only like one computation, one
Yeah,
run of then
exactly.
I believe that
Exactly.
that
Then
kind
we are
of open
yeah.
platform would be much more
Yeah.
efficient.
Then we are good. So also for the polytope computations, Stefan improved a lot, and we had a lot of theses. But for example, because we stick to exact computations, at least for the polytope computing vertices, and so this is expensive. So
Yeah,
some
that's
things some bad things do not happen by us, which might happen in other tools. But of course, it takes
Yeah,
time. Yeah, it costs something, and also if you develop, then the numbers are tight. So you can compute exact even in all representations if you want. It is slower, but it takes time to maintain. Each time you do something, you have to think
Yes,
that it
yes.
works for both, for all supported number representations. So it is really sounds simple. It is complex if you develop it. If it is well done, it is also easy if you use it. So we have regularly practical courses with students where we use this library, and it is very good that they come into the topic and then they enjoy, because there is already something to start with. So they can concentrate on the high level aspects. And yeah, so it is, we pay a bit of price for the modularity.
Yes, yes. No, I think that is extremely important.
Yeah,
That is something that I think that it should be done in the community.
yeah,
Because thinking of something like own purposes, the tool at this moment is too early. So it's need to have some kind of open.
yeah. And it was also not our aim. So we really wanted to have a library which can be used by others. And of course, we use it also. And we also try to improve the technologies, but we did not want to focus on one representation and then develop a tool that is better than all others. We wanted to rather think it as a support for other scientists. But it is very good and it's improving. So for example, the box representation last time, Stefan came to me and he was so happy, now we have a really fast box implementation. Yeah.
I have a question. So the idea of partitioning the space into smaller subspaces is actually very interesting, but so far you have to do it manually, and then you have to more or less
No,
around,
it is. I do not know that it is not yet in the release. But if you ask Stefan, he sends you the implementation. It is automated
it is automated.
because that you can check syntactically.
Okay, but is it some sort of subspace identification?
No, it is just that all the conditions appearing in the automaton are checked, and if x and y never appear in the same constraint, so arithmetic constraints like x equals y plus 5, then you know x and y are dependent. If that never happens, then you can pull it aside.
Okay, but what if you have a more general description in the sense that you have a differential equation and you can sort of analyze the A matrix and then
No, you have a differential equation, and if in the same equation two variables appear, they are dependent.
yes.
If they never appear in the same equation, then they are not dependent. So this is a very clear, syntactically easily decidable condition.
But is it still possible to do this subspace identification if you don't have this syntactic?
No, then you cannot. Not this way. There are other techniques which you can then you compute over approximatively locally, and then you check and refine according to what you have computed in the other subspaces, but that is more complicated.
Yeah, a comment on this. There do, it doesn't always apply, but there also exists decoupling transformations. So, like say x dot is a function of x1 dot is a function of x1, x2. There may exist a transformation to remove that and make it say only a function of x1.
Yeah.
So that's possible.
Yes, so we tried that also. This is basically if you can diagonalize the matrix.
That's decoupling, isn't it?
Yeah, that is the decoupling, or not only diagonals, but if you have this sequence of boxes in the middle, then you can decouple. But the problem is that you do that, and you compute locally, and then, for example, if you, in the invariant they appear together, then you have to compose them. And by composing them, you lose precision. So if you decompose, compose, you will be faster, but you will lose a lot of precision. Whereas if you do not need to compose, but can do also the intersections locally, then you are better.
That's the best case scenario, isn't it?
Yeah. So we tried the other one, but it was not very helpful in terms of the over-approximation was very big. But indeed, a very good idea. So
It's interesting, you have these situations where you can do some parts faster and then the other parts slower. It sounds a little bit like the tortoise and the hare, again, in a different story.
exactly. So also another example where this tool was used is probabilistic reachability analysis, because there you can also have the basically that was in Petri nets, hybrid Petri nets, where you also reach some sets which you can over-approximate polytopes, but there is no tool doing that. So they were searching for something with which you can compute with polytopes, but other libraries do not offer all these methods that you need, like linear transformation, Minkowski sum, and so on, safely over-approximating computations. So you can use it at different areas and not only in hybrid systems reachability analysis.
So many interesting research problems left for young PhD students to sort out.
Exactly. It's your task.
That's right. Your mission, should you choose to accept it.
Good.
Any other questions? Great. Thank you again very much. But before actually we end, this is the last talk, so we have a very small.
Oh, let me guess what is inside. Thank you. Thanks a lot.
I heard you like green.
Yes.
Thank you very much, Erika.
Thank you, David. That's very